Hello students, let us continue Chapter 12 Electricity. Today we are going to discuss our next important topic, heating effect of electric current. So before starting this topic, let us discuss how is heat produced by an electric current. So, a cell or a battery is a source of electrical energy, as we know. The chemical reactions within a cell or a battery generate potential difference between its two terminals. So, these potential difference gets the electrons in motion to flow through any circuit, that is through a resistor or a system of resistors connected to the cell or battery. So, to maintain this flow, the source has to keep expanding its energy. But only a part of the source energy in maintaining the current may be consumed into useful work, while the rest of the source energy is converted into heat to raise the temperature of the electric gadgets. So, in this way, heat is produced in any electric circuit or current. Now let us discuss heating effect of electric current. When an electric current is passed through a high resistance wire like nichrome wire, then the resistance wire becomes very hot and produces heat. Just we have discussed this. In purely resistive circuits, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. Heating effect of electric current, that is conversion of electrical energy into heat energy, is utilized in devices such as electric heater, electric iron, toaster, microwave, etc. Now, to prove the relationship between heating effect of current, let us discuss. Consider a current I flowing through a resistor of resistance R. Now let the potential difference across it be V volts. Let T, small t, be the time during which a charge Q flows across. Now the work done in moving the charge Q through a potential difference V is VQ. W is equal to VQ. We have discussed this initially. Therefore, the source must supply equal energy to VQ in time t, and hence the power input to the circuit by source is P is equal to V into Q upon T. But we know that Q upon T, charge per unit time, is known as current, flow of current. So we can write VI instead of that. Now the energy supplied to the circuit by the source in time t is P into T, power into T, that is VIT. And what happens to this energy expended by the source? So this energy gets dissipated in the resistor as heat, and thus for a steady current I, the amount of heat H produced in time t is given by H is equal to VIT. And by using Ohm's law, by applying it, H is equal to I square RT. That we can write V is equal to, so we can write V is equal to IR according to Ohm's law. So here H is equal to I square RT. Instead of writing V, we can write IR. So I square RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is, very first, directly proportional to the square of current for a given resistance. That is, H is directly proportional to I square. And second, directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a known voltage source, as shown in the figure, is used after calculating the current through it, and the relation is I is equal to V upon R. Now, regarding this heating effect relation, let us discuss an example 12.11. 100 joules of heat is produced each second in a 4 ohm resistance. So find the potential difference across the resistor. Let us start the solution. What we are given? Heat H is equal to 100 joules, R resistance is equal to 4 ohms, T is 1 second as they are saying in each second, that's why, and we have to find out V, voltage, potential difference. So from the equation H is equal to I square RT, we can find out the current relationship, that is I square is equal to H upon RT, or I is equal to under root of H upon RT, and H is 100, so therefore under root of 100 joules upon 4 into 1, 4 ohm into 1 second, and we'll have the relation 100 upon 4, that is 5 ampere, because it will be 25, and 25 root of 25 is 5 ampere. Thus the potential difference across the resistor V will be V is equal to IR from Ohm's law, therefore 5 ampere into 4 ohms, that is I into R, and it gives answer 20 volts. Now practical applications of heating effect of electric current. So the generation of heat in a conductor actually is an inevitable consequence of the electric current, unwanted. So in many cases it is undesirable as it converts useful electrical energy into heat. In electric circuits, the unavoidable heating can increase the temperature of the components and alter their properties. So, however, heating effect of electric current has many useful applications also. The electric laundry iron, toaster, electric oven, electric kettle and electric heater are some of the familiar devices based on Joule's heating. Then the electric heating is also used to produce light, as in an electric bulb. For example, here the filament must retain as much as of the heat generated as is possible, so that it gets very hot and emits light. Now it must not melt at such high temperature, so we should use a strong metal with high melting point such as tungsten. Melting point is around 3380 degrees centigrade, is used for making bulb filaments. The filament should be thermally isolated as much as possible using insulating support, etc. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of filament. Most of the power consumed by filament appears as heat, but a small part of it is in the form of light radiated. This is the working of bulb. Another common application of Joule's heating effect is the fuse used in electric circuits. It protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with the device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point. For example, aluminium, copper, iron, lead, etc. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases, and these melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1 ampere, 2 ampere, 3 ampere, or 5 or 10 ampere, etc. For an electric iron which consumes 1 kilowatt electric power when operated at 220 volts, a current of 1000 upon 220 ampere, that is 4.54 ampere, will flow in the circuit. In case a 5 ampere fuse must be used. Next, electric power. We have studied in earlier classes that the rate of doing work is known as power. This is also the rate of consumption of energy. So, our last equation gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. We have discussed the power P is given by P is equal to VI, in last relationship, P is equal to I square R, or we can say V square upon R. As we know that I is equal to VR, so I square will be V square upon R square, and on cutting we'll get V square upon R. And the SI unit of electric power is watt, denoted by capital W. It is the power consumed by a device that carries 1 ampere of current when operated at potential difference of 1 volt. Therefore, we can write 1 watt is equal to 1 volt into 1 ampere. The unit watt is very small. Therefore, in actual practice, we use a much larger unit known as kilowatt. It is equal to 1000 watts. Since electrical energy is the product of power and time, so the unit of electrical energy is therefore watt hour, WH, watt hour. 1 watt hour is the energy consumed when 1 watt of power is used for 1 hour. And the commercial unit of electrical energy is kilowatt, that is kilowatt hour. So commonly known as unit. So we can write 1 kilowatt is equal to 1000 watt into 3600 seconds. Next, example 12.12. An electric bulb is connected to a 220 volt generator. The current is 0.50 ampere. Then what is the power of the bulb? As just we have discussed the relationship of electric power, that is P is equal to VI, and V is given here 220 volts and I is 0.50 ampere. On multiplying both the things, we'll have the answer 110 joule per second, or in case of watt we can write 110 watts. So students, we have completed the topic heating effect of electric current and electric power. I hope you understood this topic, and thank you for listening this video.